Hello, Taylor. I don't know what is going on, but did you have some problem getting in?
Um, yeah, I think the password is different for this meeting than the last one.
That's
Uh,
absolutely right. It's weird. I went into Zoom and it only said it had one meeting, even though I'd set up the meeting for the whole semester. And that one meeting was for May 5th, so it wouldn't let me start it. So I started a new one, and then that worked. But somehow you got to it before I even sent the email with the new one. So somehow you got into this one. That's good.
Also, I think Zoom might be having some issues. I don't know. I was trying to install Zoom on my other computer, and like I'm just having difficulties getting to the website on that one.
Gotcha.
So I don't know.
Yeah, it was weird. I went in there and it showed. I mean, I made it last time and it had every meeting for every class from now until May 1st. And today I went in there and there's exactly one meeting in there and it's May 1st and it wouldn't let me start that one. I'm like, man, this stinks. We're getting some people in now. We've actually got a full class, so we really should have a lot more. So I'm gonna give them a little bit more time on this. Yep, another person coming in. Good deal. Yeah, this class has like 25 students, so we definitely should have a lot more than this here. Anybody have any questions while we're waiting for everybody else to stagger in? Okay. I'll give it a few more minutes. It'll take me a little bit. I'm going to try to share my screen, make sure I can get that to work since I'm not in the parking lot of a Wendy's anymore. Maybe that'll work a little better. We'll do this. Let's see here. Yes, now I have this. Now I have this. Excellent. Okay, so now people are able to get in and they can see my screen. So, all right. Does anyone have any questions now before we get started? I'll go ahead and start just because we're 8 minutes starting late. But there's not that many people in here. But feel free to just raise your hand or just start talking if you have a question for me, because I don't know how responsive this will be when you do the raise hand thing, but normally I think it's supposed to, when you do the raise hand, it's supposed to pull your name up to the top, so I'll see it. But if I miss it, you can go ahead and speak out once you put your hand up and it hasn't been addressed in a second. So last time I gave you some hints about how the scientific method worked, and how it's not really a quote unquote the scientific method. It's not very reasonable a way of stating it. Just as a quick outline, I did this in the air because I couldn't get drawings to go, but I want to show you an idea of that cyclic nature that we were talking about. So I'll do that real quick. But basically, you have often an observation / experiment. And from that, you make a hypothesis. It doesn't always happen this way, of course. As I told you, for instance, Einstein started with a thought experiment and made a hypothesis on that, and then used that to make predictions, which is what you do with your hypothesis. You make predictions. And then you test those predictions by observation or experiment. And the main thing is a scientific, got another person coming in, yay, a scientific hypothesis has to be falsifiable. And if it's really any usefulness, it needs to be able to make predictions as well. Okay. So it doesn't have to be provable. It just has to be disprovable. So as long as you got that, you're golden. And as I said, you go through this process over and over and over. in a really big paradigm like Einstein's special theory of relativity, he had more or less two hypotheses. One is that the speed of light is a constant independent of the motion of the source and independent of the motion of the observer. And the other was the laws of physics are the same for all inertial observers. And I tried to mention before that inertial observers are any observers who seem to think, based on all their world experience, that Galileo's law of inertia or Newton's first law of motion actually holds. In other words, they don't see objects accelerating unless a net external force is acting on them. Now, that might sound kind of weird. Obviously, this is one of Newton's laws of motion, so that wouldn't happen. But if you think about the Earth orbiting the sun, if you look at that as a system, you would realize, oh, wait a second, the sun is just sort of sitting still in some sense while the Earth orbits around it. The Earth is actually deviating from a straight line, so it must be experiencing a force, but you don't see any forces attracted to pulling on it or pushing on it. Therefore, Einstein would claim there is no force, and therefore gravity is a non-inertial reference frame. Okay, that's why he did that whole second part about the laws of physics are the same for all inertial observers, because he was making the argument that gravity is not going to be a force, it's going to be something different. So that's the two hypotheses. And then from that, you can do neat little derivations that allow you to find, for instance, that time will dilate, that length will contract, that every energy that's ever produced is a result of a corresponding loss in mass given by E equals mc squared. Velocities don't add the same way, all sorts of cool stuff. So that's how a really big, broad, comprehensive paradigm of thought can slowly become a theory by going through this cyclic process hundreds of thousands or tens of millions of times and never ever being found in error. Only then can you call it a theory. And before that, it's just a hypothesis or a way of understanding the universe that's currently working. Once you get a great deal of confidence in that from many, many loops around, it's no law. It just because it still only takes one experiment to completely show it's wrong. Because every scientific hypothesis has to be falsifiable. And Einstein said, no number of experiments can prove my theory right. And it only takes one experiment to prove my theory wrong. So in that case, he's using the word theory like we used to use it, sort of as a hypothesis. So again, just you're seeing the nature of using the word experiment erroneously. So that's a recap of what we did on scientific method. Anybody have any questions on that? Now, we use predominantly the what most people call the metric system, and it's actually now called the Système International, which is French. But basically, around the time of Napoleon, which was shortly after the Renaissance and that sort of stuff, people tried to make things a little more logical. So at the time, France was sort of one of the superpowers, as was Great Britain. And they were trying to get a system of units that we could use all over the whole planet. And that's when sort of like the centigrade system, which became the Celsius system, that's where that came in for temperature. And that was continued up through the 1900s when they finally made the Système International, which is also called the MKS system, which is also called the metric system. And the system that we use, our great nation, and one other nation that I know of, which I believe is Liberia. Those are the only two countries / nations that use the British system. Even the British do not use the British system, but we use it, and we're just having a hard time getting off of it. But we use the system, and what it is a system of base units, and they call it MKS because the fundamental units in a metric system. Actually, let me erase this for a second. The fundamental quantities in a unit system or a scientific unit system is in fact mass and length and time. It's also called the System International. It's also called Metrics System International and MKS. Okay, and that's because what you have is a base unit that might be, for instance, we actually call it the kilogram because the gram's so small it's not very useful, but in general they would call it the kilogram. But we use the gram / kilogram for the unit of mass, for the unit of mass. For the unit of mass. We'd use, for instance, the meter for the unit of length. That's where the M came from. And we use the second as the unit of time. That's where the S came from. So that's why they refer to it as the MKS system. And what it is a system of units where you have a system of prefixes that you can use. And each prefix is a power of 10 or a power of 1,000 higher than the one next to it. So for instance, we have, actually, I don't want to write it on here because it's huddling me in with a little too little space. Let me see if I can do it though. What I'll write is a capital T dot capital G dot capital M dot. Got another person coming in, and then kilo, hecto, deca, and then base, and then deci, centi, milli, micro, nano, pico. Okay, that's our units. If you go to the left, each letter or dot movement from one letter to the next or from one letter to a dot is a power of 10. So this one is 10 to the 1. This is 10 to the 2. This is 10 to the 3. And then 4, 5. This is 10 to the 6th for mega. 10 to the 7th for giga. And 10 to the 9th for tera. Now, these are in the front cover of your book. If you look in My Lab and Mastering, you'll see that there's a link to, I think it says cover material or something like that. So you'll find it in there. If you go the other way, it's dividing by a factor of 10. So this is 10 to the -1, 10 to the -2, 10 to the -3, 10 to the -6, 10 to the -9, and someone else came in, and 10 to the -12. Okay. So by writing it this way, you can actually do quick and dirty unit conversions. For instance, if I ask you to convert 0.000000000 0.00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 seconds. If I want that converted to microseconds, then I can do that just by looking on this graph basically that I made. So what I do is I start off on the prefix that I have, which in this case is G, and I count not the space and not the endpoints, but I count the moves. So there's 1, 2, 3, 4, 5, 6. Whoa. The thing started auto correcting. I hate it when it does that on its own. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15 places to the right. So I actually made 15 moves to the right. So I'm going to do the same thing with this and say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I know the answer is 1, 2, 3, 4, 0 microseconds. So that's the advantage of that, is you can just quickly throw it in there if you're just really needing on the fly how to convert from, say, tera to micro, or giga to nano, or whatever. You can just do that. It's too slow to do in many calculations, but it's nice to do. So this is what I would have my algebra, or excuse me, sometimes my algebra based, but my non-mathematically based physics students will do this a lot. For instance, in the conceptual physics class, that's how they convert units. You can just move it back and forth. But what we do more robustly to convert units is a little bit bigger deal. So does everybody understand what I just did there? Notice I counted the humps. I counted the moves. I did not count the endpoints. And notice also the way I wrote this is from big to small, from left to right. And if you write it that way, then the direction that you move also tells you which direction to move your decimal place. So that's why I knew not only to move 15 moves, but I also knew to move 15 moves to the right, which made my number go from really, really small decimal to actually a quite large 12,340. Does that make sense to everyone? Now, let me give you the more robust way to convert units. So it turns out, if you have a number, what can you do to that number mathematically that will not change its value? Can anybody think of anything?
Multiply by 1.
Multiply by 1, or you could add 0 to it. Those are pretty much the only ways you can alter a number mathematically without changing its value. So like I said the other night, if I have something reasonable, like my mom used to complain about me, I'm sure I was somewhat hyper kid or whatever. I know I was a pain in the butt, but she'd say my mouth is running a mile a minute. So we can use that as a data point. Let's say 1 mile per minute. That's a number. And I'll continue this one like this, so it'll look like that. So there's a number. If I want to change this to, say, miles per hour, I can do it, but the way I need to do it is by multiplying by 1. And in order to multiply by 1 in a helpful way, we have to sort of expand our definition of 1. So we can only multiply by 1 or add 0. Of course, there's other operations. We could, for instance, square it and take the square root, or we take the square root and square it, or we take the cube root and then cube it, or take the cube and then take the cube root of that. But these are pretty much the only things. So the trick is realizing how exactly is how exactly are we going to define 1 to help us. So if I say 1 is 1, you also know it's 1 over 1. But that lends you to the idea that maybe it's the same thing if you say pi over pi, because really a fraction whose numerator is equal to its denominator is really 1. Now we can get a little bit more abstract just by saying that 1 foot is equal to 12 inches. And we can get a little more abstract still by realizing that it's also perfectly acceptable to write 12 inches over 1 foot. So if you can come up with an equivalent statement between a unit you have and either a unit that you want or a unit that's on the way towards a unit that you want, then you can convert units. So let's start with, instead of the 1 mile per minute, because that's a little bit level of complexity higher than what I wanted to jump with, let's start with something like, actually, something just happened here. Hold on. All right, cool. Let's start with something a little more straightforward. Let's say, for instance, we want to know how far is a mile in kilometers. Okay, so 1 mile to kilometers. What I'm going to do is I'm going to call 1 mile over 1, because you can always write any number over 1 to make it a fraction. And the reason why I do it is because sometimes my students are not that comfortable dealing with fractions. I know they've made it through pre-calculus, they've made it through Calc 1, but sometimes they're still a little rusty with their basic fractions. I don't like that at all. Everybody should be up to speed on their fractions, but just in case, I like to do this. And then it's no ambiguity as to whether that 1 mile is in the numerator or the denominator. So what I'm going to do is I'm going to try to use not just one constant, which I can look up in the front of the book, but what I'm going to try to do is use facts that I know and a lot of people know. Like, for instance, I know that how many feet are in a mile. Do any of y'all know how many feet are in a mile? You might remember the number.
5,280.
Exactly. So if I want to make a conversion from miles to feet, then I can use a 1 as 1 mile is 5,280 feet. Or I can use 5,280 feet equals 1 mile. Now, what you have to realize in doing this, and I left off a 0 on that number there, that wasn't helpful. What you have to realize on that is when you look at what we call a denominate number, that's numbers that have units are called denominate numbers. When you look at a denominate number, hopefully you've thought maybe for a brief second, I wonder what mathematical operation is going on between, say, the 1 and the foot, or between the 5,280 and the feet. If you haven't, it's okay. But now I'm going to tell you, the operation going on between the number and the unit is multiplication. So when you say something is $500, you mean something is 500 times the unit of dollars. And in that sense, a dollar is just acting like a variable from algebra. Why is that helpful? Because when you have a string of multiplication and division problems with no addition and subtraction, that means factors in the bottom can cancel out with factors in the top. So that gives me sort of a map of how to get from miles to kilometers. If I can go from miles to feet, and then I can find some way to go from feet to, say, inches, and then I can find some way to go from inches to, say, centimeters, and then I can find some way to go from centimeters to meters, and then some way to go from meters to kilometers, then I'm done. And that's what I'm going to do now. So here I have a mile, and in order for me to get rid of the mile has to be in the bottom. So I put it in the bottom. That forces me to use the second version that I wrote, the very last one on the far right. So I'm going to say 5,280 feet. And notice what happens. This mile cancels out with that mile. Now I'm going to say, okay, well, now I've got, instead of 1 mile, I've got 5,280 feet because that's the only units that's left. Now I'm going to go from feet to inches. And you all know that there's 12 feet in an inch. So do I want to use 1 foot over 12 inches, or do I want to use 12 inches over 1 foot?
Twelve inches over 1 foot.
Exactly. So I'll put 12 inches over 1 foot. And everybody sees why. This is just like when you did it in high school, or maybe high school algebra, maybe pre-algebra, maybe pre-calculus. But you'd have like 3x squared over 5x. You know, the x in the bottom can cancel out one of the x's in top. That's what's happening here. Okay. Now this time I'm going to cross it out, but I'm going to use a different symbol so that if I look back at it later, I can tell exactly what I canceled out with what. And if I have an error, I can usually find the error a little easier. This is just things I've learned from solving physics problems for decades. So now I've got the number of inches. now I can go from inches to centimeters. And I love this particular conversion because this one's an exact conversion, as are all of these. So whatever number I put in, I started with 1, for instance. If I gave you that number to 84,000 decimal places, guess what? You could spit out the answer to 84,000 decimal places because all these factors are exact. So now I'm going to convert from inches to centimeters, and I happen to know that 1 inch is defined to be 2.54 centimeters. So I'll say 1 inch, 2.54 centimeters, and that's exact. Okay, just like 12 inches is exactly 1 foot, just like 5,280 feet is exactly 1 mile. So again, I've got another unit to cancel out, and I'm going to use yet another way to do it. This time I'm going to use a full X. So notice in this case, I went bottom left to top right, and then the next case, I went top left to bottom right. I'm just making up a new way of doing it every time. Now I'm up to centimeters, and I happen to know from that table over here, centimeters is 10 to the negative 2 meters. So you can say 1 centimeter is equal to 10 to the negative 2 meters, or you can say that 1 meter is equal to 10 to the positive 2 centimeters. In other words, 100. What I usually think of is there's 100 cents in a dollar, just like there's 100 centimeters in a meter. Okay. So I'm going to now take and put my 100 centimeters at the bottom. And by the way, I do take a screenshot of these. Actually, I make these notes in the PDF, and they go on my Google Docs page with the name that you see up at the top. Or actually, you don't see it at the top. The name for this one is PHY241N01B underscore 01112023. So you just see it's January the 11th, 2023. And that brings me up to meters. But now I've got to come up with a new symbol. So I'm going to do a curly top left, bottom right. That cancels out that centimeter. And now I can go from meters to kilometers. And I know that a kilo means 1,000 meters, which you can also get from this table again. See that the kilo has 10 to the third by it. So we can do that again. So this time I'm going to say that 1,000 meters is equal to 1 kilometer. And I'm going to find yet another way. This time I'm going to bottom left to top right, but it's going to be curly. So that's just a nice way I found over time to keep from or to allow me to figure out any errors I make and to help me not make errors. Now, how do you do this? Well, when you have this long string like this, I know that again, these are really stressing on the students who's don't like working with fractions that well. So I try to give you a way to do it. And what I do is I take all the numerators and multiply them. So I'm going to say 1 times 5280 times 12 times 2.54 times 1. And that gives me 160934. 0.4 divided by, now I do the same thing with the denominators. I go 1 times 1 times 1 times 1 times 100 times 100. And this gives me, in fact, 10,000. And the only unit that's left is the kilometer. So I write that next to it. So I do 160934.4 divided by 10,000, which is my answer that I got last time. And I get what did I do? Oh, I multiplied by 100 times 100 instead of 100 times 1,000. So yeah, it gives me 1.609344. So this is not 10,000. This would have been 100,000. Notice how when I write, small numbers, I try to put them in like little pods of 3, or when I write big numbers, I want to put the pods of 3 zeros. And there's a way you're supposed to do it. You're supposed to start from the right or from the decimal place and go out. I don't care so much about that, but if you ever have to turn in anything that has a lot of numbers like this 100,000 does, try to write them in pods of 3 so it's easier for yourself and for me to count. But we've now discovered that 1 mile is equal to 1.609344 kilometers. Does everybody get how that's done? So you're just looking for it's sort of like it's a puzzle where you're trying to find a map from the unit you have to the unit you don't have and you want. And sometimes you're lucky enough to just grab a conversion factor right off the web. I mean, we have access to that nowadays. We didn't have that when I was younger. So I have to go and look in a book, and I might find a book that didn't have units from meters to kilometers. So I'd have to, go from first meters to centimeters or something like that. So that sometimes happens. But the main thing is, long as you can find a way to consistently cancel out the units that you don't want until you're left finally with only the unit that you do want, then this works great. Okay. Now, in reality, there's actually at least 3 ways that I know of converting units. So does anybody know of a particular unit that requires you to use a formula? I think I asked you guys this last time, but requires you to use a formula to convert it, say, from one unit to another?
Temperature?
Yeah, temperature is one. Yeah, the temperature to Celsius to Kelvin or Fahrenheit to Celsius, they require a formula. So that's one way, is there's an actual formula. Another way is this multiplicative stuff, which I just showed you. So sometimes you just have to multiply numbers to cancel units and to change units. Now, another one is the unit of sound that we use. And you all know that's normally the unit of how loud something is called anybody? Got a word. There you go. It's got the word bell right in it, right? And the deci, believe it or not, is that lowercase d that you see right here. That's the deci they're talking about. So when they say decibel, they actually mean 10 to the negative 11th bells. And what a bell is a bell is the logarithm of the sound intensity in watts per square meter divided by an accepted value of the sound intensity in watts per square meter. So
excuse me, sir, can you please repeat?
Yeah, I saw you looking at that. I could tell you were trying to get me. Did you want to grab a snap of this or something?
Yes, sir. I didn't really catch it.
So that little D there, that's deci. Let me go over all of them again while I have it kind of big like this. And the first one, T, is tera, T-E-R-R-A. And the dots are very important because we're not going up by or down by 10 each time unless you count the dots. The G is giga, or if you watch Back to the Future, you call it giga. And then the capital N is mega, like Brad Pitt and Megamind. Actually, I think he played the good guy, and Megamind was played by someone else. I can't remember who. But anyways, the K is kilo. The H is hecto, H-E-C-T-O. And the capital D there is deca, capital D-E-K-A. The B is for base. The lowercase d is for deci. So that's the arrow I drew for you earlier, and I think you were trying to catch up with. So when we talk about decibels, that's the deci from decibels. The C is centi. And the M is milli. That Greek letter mu right there is micro, M-I-C-R-O. That lowercase n is nano. And that lowercase p is pico.
Thank you, sir.
No problem. All right, so we've gotten that. Now, what I want to do again, I'm not going to address my mom's mile a minute yet. I would, well, actually, yeah, I think I will. I'll go ahead and do mile a minute. So 1 mile a minute to miles per hour. Let's do this. So I'm going to first break it up into a fraction. I'm going to say 1 mile per 1 minute. Remember, you can always put a 1 in the bottom. And if you have a unit that has a denominator, then you can put the 1 next to that unit if you want. So this looks like 1 minute per 1 mile. I mean, 1 mile per 1 minute. And that's fine, right? So I want this in miles per hour. That means I don't want to change the miles at all. I only want to change the hours. Okay. Or change the minutes to hours. And obviously my iPad wants to just erase things at random. So I'm first going to realize that I can go from minutes to hours by what conversion? What's the conversion between miles and minute, or between minutes and hours? How many
minutes, 1 hour?
60 minutes is 1 hour. So you can write that as 60 minutes divided by 1 hour, or you can write that as 1 hour divided by 60 minutes. What do we want in this case?
Minutes on top.
Exactly, because you want to cancel out that minutes on the bottom. So you needed the minutes to be on the opposite side. So 60 minutes is 1 over 1 hour is what we want. And lo and behold, you see that the minutes cancel out. And guess what? When your mom said your mouth was running a mile a minute, or when my mom said my mouth was running a mile a minute, it was actually running 60 miles per hour. I hate the way I wrote that. All right, so that's a neat one. Now, let's try converting that 60 miles per hour to what we normally use in physics, which is meters per second. Okay, so that's the more common unit that we use because the MKS has a base system that's made of the meter, the kilogram, and the second. So let's try, as another example, let's try 60 miles per 1 hour. And this time I'm going to convert it to meters per second. This is also nice because if I gave you 60 miles per hour to an infinite number of decimal places, I'm going to go through exact steps so I'll get exactly the right answer so that no matter how many decimal places I put in, I can get that many out. So it's just like when I converted miles to kilometers, so I got an exact figure, 1.609344. So here we go. We have, first off, that 1 mile is equal to 5,280 feet. I have that 1 foot is equal to 12 inches. I have that 1 inch is equal to 2.54 centimeters. And then I have that 100 centimeters is equal to 1 meter. And now I've finished the numerator. I've converted miles to meters. Now I need to convert the denominator, which is in hours. And I happen to know, and you probably can figure this out too, that there's 3,600 seconds in an hour. So I'm going to say 1 hour is equal to 3,600 seconds. And this should give me what I need. Now let's check our units. I'm going to say the mile canceled out with the mile, the foot canceled out with the foot, the inch canceled out with the inch. Let's, instead of making up different shapes, I'm going to use different colors now. Let's say the centimeter canceled out with the centimeter and the meter cancel out with nothing. Let's undo that. Undo that. I said undo that. There it is. But what I did see is that the hour canceled out with the hour and left me with meters per second. So I do know the units are right. Now I'm going to do 60 times 5280 times 12 times 2.54 times 1 times 1 and then I'm going to divide that by parentheses 100 times 3600. And I get 26.8224 meters per second. So that's a good rule of thumb if you guys want to use that. Basically 60 mph is equal to, make sure y'all know that's a 60 by drawing my 6 a little better and then messing up my 0. So that was nice. Nah. And let's make it something pretty red. Now that's an exact conversion. So that's kind of useful. In fact, if you wanted to break it down into something like tens, I could divide both sides by 6. And I'd get 10 miles per hour is actually equal to 4.4704 meters per second. So that's another conversion you could use if you wanted. But all these are fair game. These are the kind of conversions you should know how to do. In fact, a large number of problems in physics can often be solved just by analyzing the units and seeing that they work right. I was once hired to do lawn work at a resort in Corolla, North Carolina when I was still in high school. I had been luckily blessed with a single course in chemistry that I failed. But it was kind of neat because I was out mowing grasses and weed eating and literally mowing down reeds and stuff in Snakeville and Swampville. And they talked to me and realized that I was, pretty approachable and had a ability to carry a conversation. So they asked me if I'd drive their trolley. So I drove their trolley and I became sort of their, person that advertised and all that stuff for them. And I had their little kids would ride and because I'm good with kids, I love kids. So they had a good time doing that. And then they said, well, hey, I heard you've been swimming a lot, and they knew I was kind of a strong swimmer. So they asked me if I'd be interested in lifeguarding. And this was a good job to begin with. Minimum wage at the time was about $7.35 an hour. And they started me off at $10 an hour. So I was pretty excited being in high school. So I started working for them. And then by the end of the second month, I'm now a lifeguard. And then one day all heck broke loose and the pool went to crap. And I went down and was reading the manual for the test kit for the pool and figured out how to fix what was wrong with the pool and just did the calculations necessary and threw the stuff in there, closed the pool as appropriate, opened it back up. And they're like, wow, how'd you know how to do that? And I said, well, it's just the manual says it right here. It's pretty easy. So they made me the pool manager then. So I literally went from $7.35, which would be minimum wage. I got a job at $10 an hour. By the end of 2 months, I was making $15 an hour just because I knew how to do unit conversions, because that's all there is when you're doing calculations for pools is just unit conversions. So it can help you a lot. And also there's sort of a tax on people that don't have math skills. For instance, if you go to Home Depot, you can see that they'll sell you these itty bitty quantities of oil to mix in your gas for weed eaters or chainsaws. And they're costing you like oil at 7 times the cost of oil. If you were to buy it by the gallon, for instance, you could get 7 times as much oil at the price you're paying for those individual containers that have always been measured for 1 gallon or for 5 gallons. And that's just a unit conversion thing. So it's very helpful to real life as well as sometimes to jobs, and you can make sense of it. Anybody have any questions on how that is? Anything about how this is working? All right, well, I'm going to do something else that shows us another really amazing number, but it also shows us how to do a unit conversion that's kind of a big deal. Okay, so one of my favorite numbers in science is the density of water. And the density of water is given the Greek symbol rho. So that looks like a P that's kind of curly, but it's actually the Greek letter rho. If you type in R in Microsoft Word and then highlight it and change the font to symbol, you'll see what it looks like. That's what symbol means when you change it, your font and Word to symbol, it'll give you the Greek alphabet. So the density of water is this amazing number. In fact, it's 1.00 grams per cubic centimeter. But it's also 1,000 kilograms per cubic meter. That's kind of neat. But it's also 1.00 kilograms per liter. And it's even very close to 1.0 ounces per fluid ounce. Isn't that crazy? All those different units. It's actually not crazy. It's basically, we realized rather early that water was kind of important to us. So every time we had to do something, we made a really simple number to deal with water. Okay, so the density of water is 1. The specific heat of water, when we learn about that, that's going to be 1 calorie per Celsius per gram, stuff like that. So in order for me to let you appreciate that, I need to show you how to do this conversion. So let's start with 1.00 grams per cubic centimeter. And I'm going to try to show that it's the same thing as 1,000 kilograms per cubic meter. So we all know the conversion between centimeters and meters, don't we? How many centimeters are there in a meter or vice versa?
100.
Yes, just like pennies. So there's 100 centimeters here, and that would be 1 meter here. But the problem is I don't have centimeters. I've got centimeters times centimeters times centimeters, which is what centimeters cubes is. So I've got to do this 3 times. Okay, so once I do that, I've now gotten rid of the 3 centimeters, the centimeters times centimeters times centimeters, so I can mark those out, but I still need to get it to kilograms. And does anybody know how many grams are in a kilogram?
1,000.
1,000.
Yep. So I'm going to put 1,000 kilogram, or excuse me, 1,000 grams down here and 1 kilogram on top. Now you can see that this gram is going to cancel out. Actually, I want a blue on that. This gram is going to cancel out on that gram. And you'll see 100 times 100 times 100 is multiplying by 1,000,000. But then you're going to divide by 1,000. So ultimately, all you get is 1,000 kilograms per cubic meter. So we've just shown the first part of that equality. Now, if y'all have been riding around lately, last maybe 5-6 years, you'll see people riding around. Often they're either companies that are pressure washing houses or companies that are working on lawns, and you'll see them have flatbed trailers with these huge rectangular, like fenced in boxes with a big white plastic, almost cubicle container inside of it. And they're about, 3 feet by 3 feet by 3 feet. Those are actually like cubic meter tanks. And that holds a whole cubic meter of water. And from this, that's 1,000 kilograms. Well, 1,000 kilograms, if you convert that to pounds, you can ask any nurse, for instance, if you want to convert kilograms to pounds, you multiply by 2.2. So you'd see that 1,000 kilograms is 2,200 pounds. And that's what we call a ton or a metric ton. Now, there's also a ton called a short ton, and that's the one that we use here in America, and that's just 1,000 pounds. Or excuse me, that's just 2,000 pounds. So that's also related to that. Now, the other part that we do to get the liters and the milliliters and crazy stuff like that is we have to realize that 1 liter is defined to be basically a cubical volume that is 10 centimeters on each side. So you can see that the volume 1 liter is defined to be 1,000 cubic centimeters, because 10 times 10 times 10 is 1,000, right? So we can now see that 1,000 kilograms per cubic meter times, let's see, 1 meter is 100 centimeters. 1 meter is 100 centimeters, and 1 meter is 100 centimeters. Then you can see that this is going to be 1,000 divided by 1,000,000, which is equal to 1,000 divided by 1,000,000. I think I got everything right there. 1 meter, 200. Yeah. So that's going to be 0.001 kilograms per cubic centimeter. So there's another measurement which we haven't done, but check this out. What if you take 1 liter and divide it by 1,000? What prefix would that be in our SI system? Do y'all know? 1/1000. It's a milliliter, right? So by dividing that, that's defined to be 1 milliliter. So I could actually say this is actually 1 kilogram per milliliter. And that's because now we can see that from this relationship right here, we can see that 1 cubic centimeter is the same thing as 1 milliliter. And if you've had kids or you're going to have kids in the near future, you'll see this. Inevitably, you'll go to the doctor, you'll get a prescription for your baby, and he'll give it to you in cc's, and then the pharmacist will give it to you in milliliters, and they'll both be the same number. Then you'll remember, oh yeah, that's right, I learned a milliliter and a cubic centimeter are the same.
Wait, I'm sorry. Those last two, hang on. The 0.001 kilogram over cubic centimeters, shouldn't it be all equal to 0.001 kilogram over milliliters? Because cubic centimeters and milliliters are the same.
Yes, a cubic centimeter and a millimeter is the same. Well, yeah, I don't know what happened. Let's do this. Okay, so I'm killing that. I'm trying to figure out why. 1 kilogram per cubic meter. That works fine. Oh. Yeah, so what I wanted to do is I wanted to take 1,000 kilograms per cubic meter, and I wanted to convert that cubic meters to milliliters. And in order to do that, I would say 1 milliliter is equal to 1/1000th of a liter. And then that is equal to how we do that. That doesn't necessarily work that way. No, that won't work either. Oh, we could say 1/1000 we already have there. And then we could say that 1,000 cubic centimeters is equal to the liter, but that just gives us 1. And so we're back where we started from. Yeah, I don't know what happened there with that one. I'm having a brain fart right now. So the last part I was showing, I didn't actually put up the thing above, but I wanted to show you ultimately. So I'll write it down here so you'll know it. And it is fact that 1.00 kilogram. Oh, I did write it there. Kilogram per liter is what's supposed to happen there. So maybe that's what I was trying to do. No, that's gram per liter. Huh. I wonder if I've misremembered. Is the density of water 1 kilogram per, 1 gram per liter? No, that can't be right. That's too small.
No, it's 1 gram per milliliter.
Yeah. Yeah, and that's the one that I didn't have on there. Yeah. I knew I'd left off one. So now going back to prove that that's 1 kilogram per liter. Oh, okay. With this, you'd have to say, okay, this is, as we found before, 0.001 kilograms per cubic centimeter. We could also call that 0.001 kilogram per milliliter. But a milliliter is 1/1000th of a liter. So I'd say 0. Well, thanks for catching me on this. This is nice. I like it when you are paying attention like that. That's excellent. Ooh. I mean, it makes me look dumb, but that's okay. I'd rather y'all be paying attention and figuring this out. So that over 1/1000th of a liter. And now you can see when you're dividing by a fraction, that's the same thing as multiplying by its reciprocal. So you get 0.001 for the 0.001 that was already there times 1,000 for the 1/1000th that was in the bottom, and that comes out to kilograms per liter, which is exactly 1 kilogram per liter. There it was. Sorry about that. I don't know what I was doing up here, but I thought it through, and quickly I was like, yeah, that works. But upon looking back at it, I might have done that too quickly without thinking it through, because clearly it took me a little bit more to show that. So it's 6:22, so it's technically class is done. I have 2 more things that I need to show you about this chapter. It's estimating, and it's unit analysis and dimensional analysis. There are on my YouTube channel, there are pages where I cover that, but I'm probably still going to talk to you about it next time. Remember, Martin Luther King Day is Monday, and there's no classes that day, but I might just make up a video on that stuff and send it to you, or I might do it in class. Either way, you'll get that covered, but you should definitely still be able to do chapter 1 homework by, it's technically supposed to be Sunday. I'm wanting to get you guys in the hang of having homework due every Sunday night by 11:59. But to be honest with you, I'm going to move it to Tuesday night at 11:59 just because of Martin Luther King Day. Okay, so feel free to ask me any questions if you don't get it. I actually, no, and since I didn't get this finished, I'm going to go ahead and push it back to, I'll push it back to chapter 1 and 2, both being due the following Sunday. But try to get as much of it done now as you can so you don't get behind, okay? I would highly recommend, go ahead.
I had a quick, well, I was going to ask, because the due dates that are in the MyLab and mentoring, I saw that there was like 2 or 3 hours worth of homework due on Sunday, and then another 2 or 3 hours worth of homework due on Wednesday. Is it all going to be like due on Sunday, or is it like spread out throughout the week like that?
Yeah, sometimes you'll have 3 or 4 assignments on a given Sunday, but they're usually either a little bit easier, or I've opened them early enough where you've had plenty of time to work on them ahead of time. Or in this case, like intro to mastering, those are extra credit ones. So what I'm going to do is take everything that's due this Sunday, which should have been just the chapter 1 homework and chapter 1 conceptual questions. I'm going to make them due a week from Sunday. And chapter 2 is still going to be due a week from Sunday. And maybe I'll take the intro to MyLab and mastering and the physics primer. I might make that due, say, Wednesday, just to give you a little bit more time. But definitely, I cannot tell you how important it is. I highly recommend that you try to do a physics problem or a couple of physics problems every day. It'll be much better for you in learning this than just wait until Sunday and doing it. So even if you just do one a day, that would be better than nothing. But I would say try to do 1 or 2 a day, every day, including Saturdays and Sundays if you can. All right. I'll wait for the last person to leave, but you guys are free to go. Thank you for coming, everybody.
Professor, I had a question.
Yes, sir. Is this Taylor or Gavin?
Gavin.
Okay.
So for our lab reports, I noticed that you kind of briefly went over it last Zoom meeting that there was something due, but it was like for your in-person class or something, the lab 1 intro to lab.
Right.
So do you want us to submit our lab reports to you as well? Because I have a whole separate canvas for the physics
For lab.
lab.
Yeah, if anything's showing up in there in lab, that's a mistake that I hadn't erased yet. So I won't have anything in my lab. Occasionally I'll put something lab related because I think it might help you with your lab instructor, but we're not linked in any way. That's just me offering the extra help to my students that have my lecture. And in some sense, it's not even fair. I usually just don't do it. So yeah, you should never see anything from lab in our lecture.
Okay. All right. Thank you.
But you can ask me questions all you want. I don't mind helping you with your lab. Just don't. Yeah. You're never going to turn anything to me in on it.
All right. I just wanted to clarify.
Yeah. Appreciate you doing that. Anyone else?
Yes, sir. I do have a question, sir.
Yes, sir.
The Zoom links. I was on the link from the Canvas sites. And nothing was going on until I saw your email. So I just want to clarify what meeting ID we'll be using for classes.
Yeah, and we're gonna have to use the latest one now, so I'll erase the one that was up there. Somehow I went to log in and it said I only had 1 meeting today. I mean, I had 1 meeting in this class, and that was May 1st. So I don't know what happened to all the meetings because I had set them all up in Zoom. So it just screwed up. And at the last minute, I had to make another one. So we'll switch to using the new one that I just emailed you. And I'll put that up in the area at the top where it says your Zoom meeting and your Zoom invitation.
Thank you, sir. Copy that. Thank you.
You're welcome. Hey, where are you at? Are you in a ship or something? Your background looks kind of shippy.
Yes, sir. Yes, sir. I'm on the ship, sir.
Okay, cool. I like it. It's like being on board the Enterprise.
Yeah, I'm on the Ford.
Oh, cool. Well, thank you for
Yes,
your
sir.
service.
Thank you for your support, sir. Have a good night.
You too. Anybody else have any questions?
Yes, I do. You said check out dimensional analysis and what else?
We're going to go over estimating, something called like Fermi calculations. Like today in my classroom, I did a calculation estimating the number of houseflies that I could fit in the classroom.
Okay.
Stuff like that, or how tall is a stack of $100 bills if it's $1 billion? How many times will your heart beat during your whole life? Little stuff like that. They're just ways of thinking. There's a great book written by Larry Weinstein at ODU called Guesstimation 2.0. If you're interested in that sort of thing, and that really impresses people, by the way, is knowing that engineers and physicists knowing how to do those things really quickly is a very impressive skill. He's written a really nice little book that tells you how to do that. And there's other books that do it too, but yeah, that's what we're going on. And you'll see when you start doing the practice homeworks and the practice tests, you'll see what it's like.
Okay. And then my second question was for the chapter 1 conceptual assignment.
Mm-hmm.
It says there's like several attempts. Does that take the best score out of all the attempts, or your latest?
That's what I got it set up where you're losing like 1 or 2 points each time you take another attempt. When we go to do our practice tests, I only count the highest, but on the homeworks, they're trying to get you to get it done as quickly as possible. But I mean, while learning the material as opposed to looking it up. So I tried to.
I'm talking about not for like if I submit an answer and it's not right and it takes points off, but is it when I'm all done with all the questions? I got like a 94.8 and it says try again for a better score.
Okay.
Does it take the best score?
Yeah, it should take the best score in that sense if it's doing that. I will
Okay.
try to double check to see how I set up the scoring to see if I'm wrong on that, and I'll let you guys know. It should have some way where it tells you what that is too. I don't know what it looks like from your side, but I'll look that up and see what I can find out. Maybe send you guys an email on it.
Okay, I appreciate it.
No problem. Hopefully y'all found the syllabus too. Finally getting around to that stuff. Anybody else? Have a good time at lab, those of you are going.
Thank you.
Thank you.
Are there any restrictions on their calculators that we can use in the class and for tests?
No, I actually allow graphic calculators, even programming calculators. You just can't use one that can store, say, photos or can access the internet.
Okay.
I mean, the open book tests are okay to use that, but not the proper.
My display, the display name is not my real name. Oh,
Okay, thank you.
No problem.
excuse me, sir.
Yes, sir.
Yeah, my display name is not my real name right here.
Okay.
I would
You're
have
not
to figure out how
Didio?
to.
What's your name?
Yeah, my name is COMNA.
Okay, gotcha.
Last, okay, you got me.
Mhm.
All right, thank you.
That wasn't Didio. I'm Didio.
I gotcha. The little green box wrapped around the Didio, so I thought that was him. It almost always corresponds to who's talking, but not always. Anyone else? All right, so if this thing records properly, it should be posted on my YouTube channel tonight or first thing in the morning, and the notes will be posted on my Google Docs page probably within 30 minutes. So you can actually download those. They'll be in a PDF format and it's coming straight off that, so there's no visibility issues or anything. Haley, did you have a question?
So I just thought, I do now, I didn't before. I came into class a little bit late, which I apologize
Slacker.
about that. But I was just wondering, were you just going over like what we kind of went over last class? Or
Yeah, I felt bad about it going so badly without having the access. So I went over the experimental method stuff, and then I went over units, base systems. I didn't go over the fundamental, what's the fundamental unit of length? It's now 1/292,452 of a second, the distance light travels in that fraction of a second. So those kind of things, I didn't tell you that, it's something like 979 billion cesium-137 nuclear transitions is now what's defined as a second. But I did tell you the basics of the units.
okay, awesome. Thank you.
No problem. See you guys. Mariana, Christian, Alvin.
I have a question.
Go for it.
Is it all right if I ask you like privately though?
Oh yeah, what I can do is I can either make a breakout room and you and I can go into it, or you can just wait and be the last person, and then once everybody's off, we can talk in private. I'll just remember to remind me to turn off the recording, because obviously that's not very private if I don't turn off the recording. All right, anybody else have anything? If you need to stay longer to ask questions, I can go ahead and put whoever needs the private time, I can put them in a breakout room, and it's no problem. But I'll do that. So does anyone have another question before we do that? All right, so who was it that had a private question? Which was it? Christian, Alvin,
Yes.
Randall?
Yeah, I had a question.
That's you, Christian? Okay, so what I'm gonna do is make one breakout room. I'm gonna invite my favorite person in there. Oh. And I'm gonna assign them to there. You've been sent an invitation. Yes.
Okay.